Hi, welcome back to Calculus. Today we're going to be looking at a little bit of physics, since physics is just math or science with a lot of math in it. Um, so anyway, we're going to be specifically talking today about work. Now, work is defined to be force over a distance or force over a displacement. Basically, if you think about it this way, if you have, I don't know, a heavy box or a dumbbell or something, it requires more work to move it farther. Okay? If you take that box and you pick it up, but you only come up 1 foot, that's less work than if you try and pick it up, above your head. Um, so distance matters. It's part of what work is. And so that's a really easy problem as long as the force is constant. Okay, so if you have a 20-pound dumbbell and you pick it up off the floor and you bring it to a height of 4 feet, the work would just be the force, or the 20 pounds, times the distance of 4 feet, and you get work of 80 foot-pounds. Now, what gets more interesting is if the force is variable, and we'll look at some examples with that here in just a second. But basically, where the force changes as the object moves, and for those we have to use some integration because the force it changes. So the work here is going to be an integral from a to b of f of x dx, where a and b are going to be those endpoints of the displacement. So frequently one of them will be 0, and then the other one will be something else. So let's start by talking about springs. Springs are such that the more you stretch them, the more force is required to keep stretching them. So that is a variable force, right? If you stretch them just a little bit or compress them, because it works either way, you just have to use a little bit of force to do it. But if you try and really stretch them out, then you get more. It requires more force. So we're going to look at Hooke's law for springs. Hooke's law states that the force to stretch or compress a string is equal to a constant times the displacement x. And so what we want to do first, our first example, is going to be to find the work required to compress a spring from its natural length of 1 foot to 0.75 feet if the constant is 16 pounds per foot. All right, so all we're going to do is we're going to set up this equation and we're going to solve it. Most of it's pretty straightforward. The force is just 16 times x. 16, there's the k, times x, again, that displacement. Now, so when I set up this integral that we had over there for work, the 16x is my force function. Dx obviously is dx. The interesting thing though is the 0 and the 0.25. Okay, because notice that in the problem we're compressing from 1 foot down to 0.75, and neither one of those numbers are on the endpoints of my integration. So the question is why? Well, with springs, you're measuring a distance from its natural state. So since the natural length of this spring is 1 foot, that's really a distance of 0. So that's why I'm starting at 0. And since we're compressing it down to 0.75, that's a displacement of 0.25. So be a little bit careful with that. If you use the wrong numbers, you're going to get a wrong answer and then be confused. So just remember, it's displacement. It's how far off, since we're talking about a spring, it's how far it's either been stretched or compressed. It doesn't make any difference which direction you're going. All right, so we just do our integration. The antiderivative for 16x is 8x squared, right? Raise the power by 1 and divide by that power. And then we evaluate from 0.25. 0, of course, is just going to give you 0. So if you plug in 0.25, you get that the answer here is 0.5 foot-pounds. So there we go. When we get to the metric system, we'll be working with joules. And a joule is a Newton meter. Yeah, there we go. Yeah, that's right. So loads of fun. Anyway, so let's continue. Okay, so I have one more example that I want to go through, and this example we're going to be lifting a bucket to the top of a 20-foot building. So here it is. A 5-pound bucket is lifted from the ground to a height of 20 feet by a rope that weighs 0.08 pounds per foot. How much work is done to lift the bucket and rope? So this is kind of a fun problem. First off, though, let's just notice that the bucket is a constant. The bucket is a constant, 5 pounds. So I'm going to break this problem into 2 parts. I'm going to find the force for the bucket, which is going to be really nice, and then I'll find the force, the work required for the rope. So for the bucket, the work is just the weight, that's our constant force, times the displacement of 20 feet, which gives us 100 foot-pounds. That part's really nice. We like constants. But for the rope, we need to pull this thing up. And the rope is going to change its weight. Every pull you make is going to change that weight. So for the rope, it's best here if we think of it again in terms of displacement. We're trying to go up 20 feet. The initial displacement is 0. So what that means is if the bucket is at some height, that displacement then is going to be 20 minus, or the new height is 20 minus x. That's how much rope is left, right? Where x is that displacement that we've had from that 0. So we want to use 20 minus x, so the weight is 0.08 times 20 minus x, and that's a variable weight. As x increases, this whole thing is going to go down because of the subtraction. So we just have to integrate from 0 to 20, 0.08 times 20 minus x dx. And when you do that, if you distribute and integrate, you get 1.6x minus 0.04x squared, evaluate from 0 to 20, which gives us 16 foot-pounds. That's the rope. Don't forget to go back and combine it with the bucket for a grand total of 116 foot-pounds. Now, one last tiny little bit of information here. This rope is a linear object. Okay, so it weighs 0.08 pounds per foot. If you had an object that depended on volume, so say you had a tank of water and the amount of water in there is changing, you're going to have to set up a function that has 3 dimensions. Okay, so if you had a box, you'd have to have all 3 dimensions, and you'll have to figure that out because the weight of that object depends on all 3 dimensions instead of just 1 here with our very linear rope. So have a lot of fun with the work, and thanks for coming.